I have to leave it right there.
He didn't go, he took it off. He had the other coach with him. It was found out.
Any extra help?
Keep tight.
Okay.
It looked like a mac and cheese.
Hey!
Yeah, except it was like master cheese versus iron man.
What are we talking about?
Super good. That he was wearing.
All mixed in. Is that last night?
I'm sure you had this.
I don't think so.
Not a cool.
I went to the
Pardon? That's much better. I can read
At
that.
some point.
I can almost read it on the back side, you know?
Huh?
Just turn it over and read the back side.
Once.
We played that game. What's the plastic I like?
Did y'all watch
I like that one.
You like this one?
I'm going to this weekend. I was doing homework.
Good for fall break.
School is my recreation.
Oh, recreation.
It really is.
It's
my break.
You break from the troubles of life.
Life.
Does that help?
I don't think Abraham's going to be here for AI to week out.
He's probably not even on this yet.
I'm looking at it. It's not a lot.
This is my only class that I can see.
I know, that's why I almost forgot.
It's a case study and it gets figured. It doesn't get better.
Everybody's here, gonna be here.
They actually like came on time. Everyone got to use that.
So, recreation is necessary to lead a human life. He also says, I'm not going to write this one down. Here's a good one that I'm not going to write down, but I'll read. If a man deliberately abstains from wine to such an extent that he does serious harm to his nature, he will not be free from blame. That's also Aquinas. He was Italian, of course, and liked his wine, but he would not condone, on the other hand, flaunting the legitimate legal authority. So that's why I didn't write it down. Okay, so we have I guess, my brother-in-law, Neil Mixon from Austin. He's visiting here. My number 2 son is getting married tomorrow, and so family is in town. He's my wife's brother, little brother, and he's a physics major, going back to college.
Need a pound on that.
It's very
All right, so, and he's read the textbook, and we've talked about this. He knows my enthusiasm for Rizzi's work, and in fact, we've been talking about it since he got here yesterday. So, just as it stopped. Okay, so chapter 3. What was the topic of chapter 3?
Energy and
Sorry, momentum. Right. Yeah, you're skipping ahead here. Yeah.
I'm very excited about this chapter.
Mr. Jackson, chapter 4.
Force.
Force. Okay, chapter 5.
Energy.
Energy. Yeah. All right. So notice the order of topics. Impetus is first. Why?
The cause of locomotion.
It's the cause of locomotion. Right? If you're going to understand locomotion, you got to understand the cause first. And force comes after impetus, naturally speaking, because
The cause of impetus.
it's the cause of impetus, right? Okay, now we're getting to the topic of kinetic energy, Work-Energy Theorem. Finally, an application for the dot problem. Back that is something that we learned back in chapter 2. Okay, so let's. What is kinetic energy then? Again, that's something you'll need to memorize. Remember, the inside front cover is a good place to go for that, but it's in chapter 5. Memorization is not the end of learning, but it's a tool. So, what is kinetic energy?
The rate of transfer or the intensity of impetus.
Yeah, across a distance. Did he say that at the end? Across a distance.
The body across the distance.
Yeah, of a body. So it's related to a body, a substance, a changeable thing. The rate of transfer of the intensity of the impetus across a distance. Okay, so let's take an analogy here to moving sand over distance, and I have different means of moving sand. I could have a teaspoon held by a runner, or I could have a wheelbarrow pushed by somebody, obviously going to be slower, or I could have a dump truck that could be pretty fast, or I could have a Porsche that has much less capability to handle a load but goes really fast. So what is the most efficient means of transferring sand? Well, it's a combination both of load and speed, right? If the dump truck has a governor on it, it can carry a lot but not go very fast, but it could be the best means. So in that example, you have some measure of what you're moving. That is the load times some speed. Okay. Now on the what's that?
He was trying to argue that a plane would be better, and I was saying that it would be the same issue because you could say a cargo plane versus a jet.
Right.
It's the same issue as a dump truck versus
A
a
Learjet or something, right? Right.
Yeah,
So
but it's still not going to move as
It's got
fast.
like more than twice the capacity.
Plus, it depends on how far you're going. If you're going like a mile, plane's not really worth it. Because it would take all the time to get up and get back down.
So it's not constant speed.
Still have huge capacity.
And it wouldn't
You're
be
not
traveling as fast as it would
abstracting
be.
I can tell the fall break is welcome. All right. So let's consider, what is it if we're not transporting sand, we're transporting in this case, Mr. Covington, what is being transported here?
The body.
Yeah, okay, the body is, in this case, is the thing that's transporting something, right? It's the rate of the transfer of the impetus. The momentum is the measure of the impetus. So it's the momentum. The body carries its momentum with it, right? It's like a turtle carrying its shell. The momentum is what causes it to move, but it carries it with it. Okay. Now the rate. Well, a massive body, the speed of its motion depends on the momentum. That's the kicker here. The speed, according to Buridan's law, is P over M. So by this simple argument, this would say the kinetic energy is P squared over M. Well, not quite. Something's not quite right. Which would be mv squared. Something missing here. And you know the formula for kinetic energy is a half. So where does the half come from? Did you figure that out?
It's
Mr. Flanagan.
because the momentum's going to be the average velocity.
Out of the way. The speed depends on the momentum. So think about it this way. What if we had a body that has a certain speed, and now I increase its momentum by a little bit? What's the increase in the kinetic energy? Well, it's the speed times the increase in momentum. That's the proper relationship. The deal here is that the speed depends on the momentum, right? It's variable. The more momentum you have, not only are you carrying a heavier load or more stuff, but you're also carrying it faster. So the speed depends on the momentum. And so what we have is that if we increase the momentum a little bit, then we increase the kinetic energy in proportion to that increase. And the proportionality is the speed, the P over M. Okay, so this is, in other words, is like a differential equation for the kinetic energy, which requires us to put a half here. Because if I take the derivative of the kinetic energy with respect to momentum, I get a 2p over 2m, right? Or just p over m. That factor of 2 comes about because of the variable speed. The speed itself depends on the momentum. So not only you have a twofold effect if you change the momentum. Not only are you carrying more momentum, but you're also carrying it faster. And so hence the factor of 2. It's a little bit like looking, if we were, maybe that's not the best analogy here because we haven't gotten into the integral calculus yet. So I'm going to stop that one at that point. So this argument gets you to within a factor of 2. Now he shows in detail how to do that. He talks about a massive body which has some momentum which is being removed from the body by some force. And so it's being slowed down to 0. And so he calculates the little incremental change in the kinetic energy the whole time. Or he does it the other way around. I can't remember. It starts from rest and moves up. Which way does it go in the text?
Second one.
Okay. So in that, he demonstrates the factor 2, how that comes out. It's easy to do with calculus. If you don't do it with the calculus, you do it the way he did it with the book, you can demonstrate that there's a factor 2 that comes in here. So it's another measure of what is more generally the kinetic activity of a body. One measure is the momentum. This is a different measure. If we know the momentum, we can measure kinetic energy. So it's a different way of presenting it. So one way that it's different, what's the difference between the kinetic energy and the momentum as measures of the activity of a body? Mr. Flanagan.
Momentum is a vector and kinetic energy is a scalar.
Yeah, momentum has a direction, whereas kinetic energy has no direction associated with it because the direction is built in to it, right? You're talking about how do you transport momentum, but it's along the direction of motion. So you're already moving it along its own direction. So the direction is built into the kinetic energy. So what if we have two bodies now moving? Let me go back to, oh man. Let's go back to our binary collision problem. Let's consider the case where these two masses are moving towards each other at the same speed, and they're going to collide. So each has a momentum, but the system as a whole, what about the system, the total momentum of the system? What is the total momentum in this case? If the speeds are opposite, if the velocities are opposite.
It's the combined momentum.
The combined momentum is how much? 0. So judging from the momentum alone, you can't tell there's anything going on in the system. If you talk about the total momentum of the system, it doesn't reveal anything about what's going on inside the system. But how about the kinetic energy? What is the kinetic energy? So also in terms of 1/2 mv squared instead of p squared over 2m. Well, they add. The kinetic energy is always not negative. There's no cancellation of kinetic energy. It always accumulates. So the kinetic energy would always be adding together. So the kinetic energy is a measure of the activity of the system that reveals to us that something's going on, whereas the momentum, as far as we can tell from the total momentum, nothing is going on. So here's another way of looking at it. Let's look at the inelastic collision. So let's suppose this is before and after. Now they come together, we stick some gum in between them, and they come together and they stick. So what's the momentum now? 0. Nothing's happened, right? How about kinetic energy? In this case, nothing. There's no kinetic energy. It stopped moving. So we've lost kinetic energy. The momentum remained unchanged, but the kinetic energy changed. So there was a loss of kinetic energy. Now something else happened in this system. What else happened? We have that gum. Gets squashed. The shape? Heat. Gum is hot. The loss of kinetic energy is somehow related to the generation of heat. So that we will come to study more in thermodynamics next term, the relationship between motion and heat. Okay? So there's a hint about it there. So in this case, the loss of kinetic energy, it loses kinetic energy, is mv squared. That's how much it loses. It loses all of its kinetic energy. Delta K over K before is -1, right? It loses all of its kinetic energy in this case. Now how about an elastic collision? An elastic collision is one, so this is inelastic. An elastic collision is one there's the before. Okay, now an elastic collision is one where the kinetic energy is unchanged. So the total momentum before is 0, and we want the total momentum for all collisions to remain unchanged. That's a basic observation of binary collisions. The total momentum of the system is not changed. But we also want for an inelastic collision that the kinetic energy is unchanged. So the kinetic energy here before is mv squared, right? 1/2 for each one. So how can I arrange the outgoing particles so that the total momentum is 0 and the kinetic energy has not changed? There's only one way. So what is that? What are the velocities of these bodies after the collision?
Equal and opposite.
Yeah, they're equal and opposite. That must mean that they have the same momentum. So the total momentum is still 0. But not only that, they have to be exactly the same values before. Minus v and v. They swap. So now the kinetic energy is mv squared. That's the only possibility that will preserve both momentum and kinetic energy. So delta P is 0 and delta K is 0. That's characteristic of an inelastic collision. I'm sorry, elastic collision. So we had this introduction to kinetic energy back in the chapter on momentum where we considered binary collisions, and he didn't explain what kinetic energy was there. That's the one place in the book where he's actually using something before he explains fully what it is. That's the only time. Now you have a better understanding of kinetic energy. But you notice that there are lots of collisions which might occur that while it could preserve the total momentum of the system, does not conserve the kinetic energy. Right? The inelastic is one case. There could be something else in between. So another possibility, here's something in between. So we have the before is what we had here. And an after. Let's suppose we had an after like this that moves minus v over 2 and plus v over 2. So how about the total momentum before and after? Any change in the total momentum?
Yes.
No.
No.
Right. No. The momentum is 0 before, 0 afterwards. The momentum doesn't change. But how about the kinetic energy? What's the kinetic energy before? Again, that's mv squared. And what's the kinetic energy afterwards?
mv squared over 2.
Yeah, so it's 2 times m, 2 times 1/2 times m v over 2 squared, right? You got two masses. Each one of them has 1/2 mv squared. So there's all these factors of 2. So it's mv squared over 4. So what's the change in kinetic energy? Well, you lose 3/4 of the kinetic energy. The delta K over K before, what fraction of the kinetic energy is lost? It loses most of the kinetic energy, but not all of it. So this is someplace in between elastic and inelastic. A perfectly inelastic collision loses all of its kinetic energy that's possible. It can't lose any more and still conserve momentum. The perfectly elastic collision loses no kinetic energy. Realistic collisions are someplace in between. Yes, sir? Mr.
Why
Flynn?
is the kinetic energy before not 2 mv squared?
It's 2 times 1/2 mv squared. Each body has 1/2 mv squared, and there are 2 of them. So it's mv squared. Thank you for asking, though, because I do make mistakes. All right, so it lost most of its kinetic energy, and something in between, so they come together and they move out, it's lost kinetic energy. The total momentum hasn't changed. It's still 0, but it's lost something. So the kinetic energy is a measure of the kinetic activity of the system, which adds in this way, which is helpful for us in studying systems. The fact that it doesn't have direction is a bonus here, right? It adds to the different character of the measure. Okay. All right, so now let's go to this interesting example in the book. He reviews friction in this chapter. I did it in the last chapter. I talked about the laws of friction when we were doing chapter 4. That's okay. So now he does it in the text. So let me ask you a question. He takes this example. So so I have this book on the table, and what impetus does it have?
0.
Yeah, you can look at it and see it's not moving, right? You wait a while, no, it's not moving. So it's reasonable to conclude it has no momentum. All right, I want to give it momentum. I want it to move, so I'm going to give it momentum by exerting a force. Okay, so I push on it, and now I have to give it a sufficient force that's going to start accelerating. Actually, what happens, of course, is that I give it impetus. The force gives impetus to the body, and it's the impetus that moves the body, the momentum. Okay, and as long as I continue to push, give it an unbalanced force, it will keep gaining impetus, and as long as it keeps gaining impetus, it will continue to accelerate. But now at some point, let's suppose once I get it moving, I back off a little bit on the force. And I'm maintaining a steady velocity. So let's look at the forces involved. And there's friction present, obviously, friction present, right? Because I'm still pushing on it, but it's not accelerating, so there must be another force. So let's diagram the forces. Well, there's the force, the push, and what kind of friction is present?
Kinetic.
Kinetic friction, and how would I diagram that?
Opposite direction of motion.
Opposite to the direction of motion, right? It's moving this way. Opposite to the direction of motion, and so the kinetic friction. So we know at this point I have to push just enough to balance the kinetic friction if this thing is going to be moving steady. That is, the speed doesn't change. So the force of the push actually counterbalances the kinetic friction, the force of kinetic friction. Here's the question. So we said that the magnitude of the push, the force of the push, is equal to the magnitude of the kinetic friction. Implies there's no change in impetus. So it just moves. Uniform linear translation, right? Uniform motion. Here's the question. What's moving the book?
It's impetus.
Mr. Disharoon, say it louder, please.
It's impetus.
Impetus, yeah. Why is impetus moving the book? Why do you say that? At least you read the book, right? It's in the book. Do you have any better answer to that?
It's a uniform motion.
It's uniform linear translation. What is impetus?
Ability to keep moving at a constant speed.
No. You're not quite there. You have to have the definition better. But what's the short definition for the impetus?
It just keeps moving at a constant.
Not just keeps it moving, it moves it, right? Impetus moves the body. It's a quality of the body that moves it. So, but the short form of the definition is?
Cause of locomotion.
Thank you. Cause of locomotion. Okay, it's moving. What's moving it? Impetus. It's always what moves it. Impetus is the only cause of locomotion. This thing moves because it has impetus. It got impetus because I was pushing on it earlier in an unbalanced way. That is, the force that I was pushing on it was not balanced, and so I gave it, there was a net force acting on it. It acquired impetus, as a result, it accelerates. And now I've gotten to the point where I'm just kind of backing off, and I just balance the force of kinetic friction, so which we know it's balanced because it's not accelerating. There's no change in the impetus. Okay, so impetus is moving the body, which you gave it earlier by pushing on it. Kind of weird. All you're doing is balancing the friction so that the friction doesn't slow the book down. You're balancing the effect of friction. And that's what you're doing. That's what's happening when you're pushing that book. Your push counteracts the drag of friction so that the book's impetus can remain unchanged. Okay, so now let's observe this. Let's remember what happened when we did the throwing the body up in a gravitational field. Remember, we went through this process of describing the motion. So let's go through it again. How about let's begin just by dropping it. What happens in terms of the basic principles of locomotion? Impetus, force, mass, when I drop this thing. Somebody like to go through this. It takes about 20 seconds to do it, right? Maybe 10 seconds. You don't have to be fast about it. Mr. Vester.
You drop it, gravity imparts force on it, the force gives an impetus downwards until it finally hits the ground. It gains more downward impetus as it goes.
Yeah, it continues to gain impetus because the force continues to act, so the result is it accelerates, right? The process is the impetus that it gains in between. Okay? So in that case, the force is downward. And what direction is the motion? The motion is downward. So I could talk about a displacement, a change of position. So let me draw this a little better here, delta R. So I start up here, and I end up down here. So that's delta R. No, wrong one. No, I want to do that. I'm still learning how to use this thing. No, not going to let me do that. Okay. I'm going to put the displacement, write it up here. I want this clear to be the displacement. So the force of gravity is in the same direction as the displacement. That's one case. And what happens? It accelerates. Does it have more or less kinetic energy afterwards? Is kinetic energy increasing or decreasing? Increasing. Increasing. So delta K is greater than 0. It's increasing kinetic energy. How about the other case, where the thing is moving up? I throw it up. It starts down here. I give it an initial impetus in the upward direction. The body moves upward. The displacement is up. Didn't want to do it down there. Let me try this again. Okay, this is where it was. And then it moves up to here. Displacement is upward. And which way is gravity acting the whole time? Downward. So, in this case, the motion is opposite to the force. What happens to the kinetic energy? It's decreasing. The force is draining impetus from the body, and the body is decreasing in its impetus, hence it's decelerating because it's got less impetus as it goes up until it reaches a high point when it's got no impetus at all. All right, but we have two different situations. The kinetic energy is increasing in one and decreasing in another one because of the relationship of the force to the displacement. What if I have a force? Let's remove friction from this table. Let's have an air track. Now, what forces are acting on this book? Well, then, in that case, there's the gravity and the normal force, both vertical forces. If I displace this thing, so I slide it, and remember it's frictionless, so it continues to slide. What happens to its kinetic energy? If I get a cart moving on the air, what's that?
It remains the same.
It remains the same. There's no change in kinetic energy. It's a voice I didn't recognize from the classroom. Mr. Mixon. Okay, so we have displacement now is perpendicular to the forces. So delta R is this way. And the forces are vertical. What happens to the kinetic energy? It just slides. It doesn't lose kinetic energy. All right, so this is getting to be a pattern here. What mathematical description, what mathematical thing do we use to describe the relationship between two vectors, whether they be in the same direction or the opposite direction or perpendicular to each other? What was the mathematical object we used to describe that in the second chapter? The dot product. So this dot product of a force acting on a displacement. So now in this case, if the force is constant, so F is constant, then we can say that the force, the dot product of the force with that displacement is called the work. Done by the force. And this results in a change in kinetic energy. The dot product, the work, that is the force dotted into the displacement, corresponds to an increase in the kinetic energy. If the force and the displacement are parallel, the kinetic energy will increase. If the force and displacement are opposite, then the dot product is negative and it will decrease kinetic energy. If the force is perpendicular to the displacement, then there's no change in the kinetic energy. What is the name of this? Anybody know?
The work theorem?
Pretty close. It's not the work theorem, it's the K on the right-hand side is an energy. Work-Energy Theorem. This is the Work-Energy Theorem. Does the Work-Energy Theorem apply to all kinds of forces? Now, he goes on later in this chapter to consider two basic kinds of forces. What are the two basic kinds of forces that he considers in this chapter, Mr. Jackson?
Conservative and non-conservative?
Conservative and non-conservative forces. Does the Work-Energy Theorem apply equally to conservative and non-conservative forces? I have some no's, I have some yeses, I have some waiting to see what's going to happen before they vote. This is where the clickers would come in handy, right? Anonymous voting, yes, no. The Work-Energy Theorem applies to all forces, regardless of whether they're conservative or non-conservative. Let me write that down explicitly because I really want you to remember this. The Work-Energy Theorem applies to all forces. Conservative or non. Oops, not none, non. Conservative or non-conservative. That's very important. Now there's an aspect for conservative forces we haven't really discussed yet. There's an aspect of conservative forces that makes them different than non-conservative forces, but it's not the Work-Energy Theorem. The Work-Energy Theorem allows you to calculate the change in kinetic energy. If you can calculate the work done, then you can calculate the change in kinetic energy. Okay. Yeah, I'm not going to do that yet. Let's go on. Okay. So, now let's consider these two basic kinds of forces. All of the forces we have considered fit into one of these two types, two kinds, conservative and non-conservative. So, how do we know the difference? What's the distinction between them? There's a couple of different ways of expressing this. Somebody like to try? Yeah, Miss Swanson sitting quietly in the back. What's the difference?
One releases heat and one doesn't.
Good, okay. That's one way, right? So an example of which is which? Which is non-conservative?
Non-conservative would be the one that releases heat.
Okay.
And conservative would be the one that doesn't.
Gravity is which?
Conservative.
Conservative. Give me an example of a non-conservative force.
I think they said in the book, like when you push a box,
Yeah.
It releases heat, like there's friction.
Friction.
So.
Friction is non-conservative. Right. So an example of a conservative force is gravity, and friction is a non-conservative force. And the way she is talking about distinguishing between them involves the release of heat. Okay. Is there another way of characterizing whether a force is conservative or not?
If it's conservative, all of its work can be converted to mechanical energy.
All of its work can be converted into mechanical energy rather than heat.
Yes.
Right, for example. Right, okay. So it's a little bit the same. Right, a little bit the same. Is there another way? Difference between conservative and non-conservative?
A conservative force would speed things up, but a non-conservative force would slow them down.
Okay, let's think about that. Gravity, we said, is a conservative force. If I throw it up, it's acting opposite to the displacement. It's slowing down. It's losing impetus. But we say gravity is conservative. Right? So that didn't quite work. Okay.
Kinetic energy is not conserved.
Kinetic energy is not conserved. No. Kinetic energy was not conserved in this example, right? Gained kinetic energy or lost kinetic energy. That's a conservative force. Okay. All right, how about this? That example of pushing the box around. Let's calculate. In that case, we have a circuit. Let's go draw a square, and I'm going to push the box around the square. I'm going to start at A, B. What's that? D. You seeing it now? Path dependence. Go ahead, Ms. Ma.
Okay, let me make sure I know exactly what you're talking about.
Yeah.
Okay, so non-conservative forces like friction are dependent on the path.
The work is dependent.
The
on the path.
work is dependent. It depends on the path taken by the body they act on.
Right. Whereas
So the example that Rizzy gives is
Yes.
if you're moving a piece of furniture in a room, would you rather move it around the entire room or directly to the spot where you want the couch?
Everybody knows the answer to that, right? Anybody who's had to move furniture around knows the answer to that question. Okay, so let's take the example of friction. Let's do kinetic friction. And I take a body, and this is on the floor. And I take a body, and I push it from A to B. So I have a body here, and this is only motion in the floor. There's only one force acting horizontally, and that would be friction, right? Kinetic friction. Which way is the kinetic friction if I'm moving it from A to B? Which way is the kinetic friction? It's opposite. And it's proportional to the normal force, right? So it's just the same all the way across. So what is F dot delta R? Well, the kinetic friction is the same all the way across, and delta R is just the distance traveled from A to B. So let's just say it's D. And is it positive or negative? The work done by friction?
Negative.
Negative. It's opposing the motion, right? F dot delta R is negative. Okay, now that's from A to B. So that's the work done from A to B. How about the work done from B to C? Now the body is moving up this way. The motion is that way. Which way is kinetic friction?
C to B.
Yeah, it opposes the motion, right? Tries to slow it down. Kinetic friction wants to stop the sliding. What's the work done from B to C? If the distance is the same, it's the same. The force of kinetic friction times D with a negative sign. How about all the way around? A to B to C to D. Coming or back to A again. 4 of those, right? Keeps adding. It's always negative. The work done by friction is always negative or 0. Static friction does no work, but kinetic friction always does negative work. So kinetic friction does no positive work. Maybe that's the way to say it. Friction does no positive work. You can only do negative work or 0 work. So if I go all the way around there, it's going to depend on the force of friction and the path, the distance that you traveled. That 4D is the perimeter of the square. So it's the force of friction times the perimeter. So if you want to minimize the amount of work you do, you minimize the perimeter, right? Or you just stay put. You know, if you're going to come back to the same place, you don't move it, right? So if I left it at A, if I go A to A without going anywhere, what's the work? 0. So the work done by friction depends on the path. It's the force of kinetic friction. In this case, the work done by the kinetic friction is just the force of kinetic friction times the path length. So you want to take the shortest distance. And the same would be true from A to B. If I go from one point, let's call it E to F, I have a point E and a point F. And I go straight, or I take a kind of circuitous route. Right? Does the work done by friction depend on the path? The longer path obviously requires more work. So this depends on the path. So for a force where the work depends on the path, that is called a non-conservative force. The reason for the name is not quite so obvious at first, but we'll get to that. So a force whose work does not depend on the path. Did I say that correct? A force whose work depends on the path is non-conservative. A force whose work does not depend on path, but only in points, is conservative. Let's do the same thing with gravity now, but let's make it a vertical trajectory. We pick it up, move it over here, lower it down, move it back over here. Okay, and it's sliding on the horizontal legs. There's no friction. Let's just do gravity by itself. So let's just consider gravity. So I pick it up, I displace it, lower it, move it back. No friction. Let's get rid of friction. Let's just consider gravity alone. So this is now up. Okay, so let's go A, B, C, D. Okay, so the work done from A to B, all right, which is where the displacement is up, and what is gravity doing? Pointing down. Minus mgd, right? Force of gravity times the displacement. How about the work from B to C by gravity now? Only gravity is acting here. So this is just the work of gravity in each one of these. If there are other forces present, for the moment we're ignoring the work done by them. So how about from B to C? Zero. Because?
There's no movement in the vertical direction.
Yeah. The gravity is acting down. The displacement is horizontal, so there's no sense in which the displacement is moving in the direction of the force or opposing the force. How about C to D?
mgd and gd.
Yeah. Oh, it's positive. We finally found a work that was positive. Right? This is when it's moving in the direction of the force. That's like when we dropped it. The displacement's in the direction of the force. We get positive work. The kinetic energy would increase it on this stage. And then from D to A. Yeah, we said no friction on the floor, so. Okay. So, a couple of things. A to B to C to D, back to A. What's the net work done by gravity? Zero. That's true for a conservative force. The work done on a closed path by a conservative force is zero. The net work. That's the same statement as the previous one. So there's two ways of doing this. One is to say it's path dependent or not path dependent. An equivalent way of saying it is that if I move it around some arbitrary path and come back to where I started from, then a non-conservative force will have some non-zero, negative, will always be negative work. Whereas a conservative force, the net work done by a conservative force will be zero. You get back as much as you put in, is one way of saying it. Okay. Okay, so the work-energy theorem applies equally to conservative and non-conservative forces. All right, now this theorem about the conservative force, very interesting. In other words, there are forces, if I move it from A to B, that the work done in going from A to B depends only on the positions. A and the position B, not on the path. So that means there's a very simple way to demonstrate that if it doesn't depend on anything in between, it only depends on where I start and where I end up, that in fact the work from A to B is a function of where it ends up, subtracting the difference in a function from where it ends up to where it began. This statement about that the work depends only on the path is equivalent to saying that there is a function of A minus a function of B. Let's see, I may have that backwards. Let me instead of naming those V, let me put in some kind of function G. Unknown function, as yet unknown function. This is equivalent. The fact that it doesn't depend on path, it only depends on the endpoints, means that I can write a function which is only a function of the endpoints, and that the difference in that function, the value of that function in the two places, is a way of calculating the work. Let's see, so and remember the work done from A to B is related to the change in kinetic energy, right? Let's go back up here. Okay. So if the work done is related to the change in kinetic energy, and the change in kinetic energy is related to the change in this function, that's an interesting thing. The work is the change in kinetic energy. The change in kinetic energy is related to this change in this function. Hence the concept of potential energy comes about for conservative force. So potential energy exists only for a conservative force. It is the potentially kinetic energy, and hence the term potential energy. So if I take a block on the floor and I lift it, I'm doing, gravity does what? What kind of work is gravity doing? The displacement is up, the force of gravity is down, so what is it's negative. Now if I let go of the block, in some sense that potential exists for it to have positive kinetic energy going down. Right? So the work that I have done against the gravity, I have to exert work against gravity. I have to also do work. Now going to show up as positive kinetic energy of the body. It's potentially here. This has potential kinetic energy. But where does the potential energy actually exist? Where does the potential energy exist? Well, it's not in the body itself, like kinetic energy would be. It's not in the body itself because it exists only by virtue of being near the Earth. So the potential energy is not simply a property of this body, but is a property of the combination of this thing and the Earth together. So it's a property of the system. The system has the potential to create kinetic energy by virtue of the force that exists from the Earth onto this object. Okay, now how do we know that something has potential energy? Well, you let go of it, right? You let go, and it acquires kinetic energy. So potential energy is called energy by analogy. So here's another analogy. It's an analog. We've encountered a lot of analogies. Now remember, with analogies, we have a prime analogate. There's always something it points back to. What does potential energy point to? Kinetic energy. Very good. So, the prime analogate, oops, of energy of any form is kinetic energy. Every time we will investigate in this following year different forms of energy, it will always be to relate it back to kinetic energy. How do you know that something has potential? Well, you let it become actual. You let it do something. So we'll look at the energy stored in an electric field because it can create kinetic energy by moving something, right? It creates a force. The force gets it accelerating. It gains kinetic energy. It does work. So kinetic energy is the prime analogate for energy. And if you ever want to talk about energy in terms of physics, like we do this stuff, energy has got to point back to kinetic energy. That's the way we know about energy, is through the kinetic energy. It's the prime example of energy. And all other forms of energy are going to point back to that, including heat, for example. We talked about heat, and we encountered this situation where an inelastic collision generates heat from the lost kinetic energy. Again, and you could have it in the reverse. You could have that gum could be an explosive, and explodes, blows the two things apart. They have now kinetic energy. What they had before was potentially kinetic energy in some form. It was a chemical potential energy, right? How do you know if something has chemical potential energy? Well, if it explodes, it releases kinetic energy. Then gives the thing, makes it move, and you can find then the kinetic energy that results. So kinetic energy is very important. It's the prime example for us of energy. So every extension that we have later, the different forms of energy that we talk about, form energy in different forms, it points back to the prime analogate. However, there's something very important here, both for momentum and kinetic energy. These, under certain circumstances, can be conserved, or we also talk about total energy. I haven't had time to construct the total energy from the sum of kinetic and potential energy for conservative force. But in some sense, kinetic energy can be conserved, or the total energy can be conserved. Momentum is conserved. But you might get the misimpression about these things. What is the momentum? Is it a substance? Is momentum a substance?
No, it's a measure.
Careful. It's a property. It's a measure of a property. Momentum is not a substance. It's a property of a substance. Kinetic energy, is it a substance?
No.
It's a property of a substance. Total energy, is it a substance? No. It's a property of a substance, or a measure of the property of a substance. So we say energy flows from one place to the other. Be careful. You might start thinking that it's like a substance. It's a fluid that flows from one body to another body, right? That's wrong. It doesn't work that way. And in fact, it was trying to fix that error. That error itself led to a lot of problems in the early days of thermodynamics, trying to look for a fluid that flowed from one body to the other, like a substance would flow. And they called it caloric. And they were looking for this stuff that was flowing from one body to the other, right? Because they thought they were looking for a substance flowing from